Okay, so we're starting out with quadratic equations. So this comes down to factoring. It relates to the zero product property. So for this first one, we want to solve x squared minus x minus 42 equals 0. So remember, this is kind of the shortcut factoring method, meaning that's all we need to do is find two numbers that multiply to negative 42, but when you add them, you get negative 1. So the constant term, we're looking for factors, and we're looking for them to add to the coefficient of the x in the middle, which, since it's just a minus, is minus 1. So that's going to be negative 7 and positive 6. So it factors into x minus 7 times x plus 6 equals 0. And the reason we're able to solve that is the zero product principle. So I'll write that down a little bit after. But basically, either x minus 7 has to equal 0 or x plus 6 has to equal 0. So now we've reduced it to two linear equations. So we just have to add 7 to both sides here in this equation and subtract 6 on both sides here. So we get our two answers, x equals 7 or x equals negative 6. And so this step here, to go from here to here, is from the zero product principle. And what that says is if you have two things multiplied together, it doesn't matter what they are. In this case, they're two algebraic expressions in the form of linear factors, then one of them has to be 0. So if a times b equals 0, then either a is 0, b is 0, or both are 0. So that's what we're invoking to find the answer there. So 7 and negative 6. Okay. So really just one extra step past the normal factoring. Okay, number 2 is going to be very similar, just a different factoring technique. That's all we need to do for number 2 is appeal to the greatest common factor. So here we want to solve 6x squared plus 12x equals 0. So what is the greatest common factor of 6x squared and 12x? 6x, yeah. So we can take out a 6x, and we get x plus 2. So a lot of times I will see students forget about one of the solutions here. We do have two things multiplied together, the 6x and the x plus 2. A lot of times I'll see people just write down x equals negative 2 as the answer, but remember, we have technically 6x equals 0 or x plus 2 equals 0. So 6x equals 0 only if x equals 0. And the other one, you just subtract 2, so the answer would be x equals negative 2. How about Nita? How are you doing? So those are our two answers, 0 and negative 2. Any questions there? So again, a lot of this just relies on our ability to factor. Number 3, they talk about the square root property. So slowly building to the quadratic formula. So the square root property, let's write down what that is. Basically, this says if you have something of the form x squared equals k, where k is positive, or k is non-negative, let's say. If k is not a negative number, then you have two solutions, namely x is plus or minus the square root of k. Right? So like, for example, x squared equals 9, that would say that x is plus or minus the square root of 9, which would be x is plus or minus 3. So you have two numbers that you can square that would equal 9, positive 3 or negative 3. So, and number 3 here, our problem looks a little more complicated, but really in fact is not so different. So the first thing we want to do is we want to isolate that x squared, and we can do that by subtracting the 9 and then dividing by the 5. So isolate the thing that we want, because we cannot apply the square root principle until we get that x squared by itself. So we have 5x squared equals 15. We divide by 5. So now we have x squared equals 3, and by the square root principle, x will equal plus or minus the square root of 3. That doesn't simplify at all, so we just leave it as is, square root of 3. It says use a comma to separate the answers, but I do believe it will use the plus or minus. So plus or minus is just a shorthand to write down two numbers, right? So let's check it, plus or minus, and then square root of slash square root. Yeah, slash square root 3. And there we go. Makes sense? So, you don't have to do slash square root. I just like the commands, right? For each one, anytime you're in the box, there's the point and click that will give you the symbols as well. Okay. So notice when we're looking at the square root principle here, I've written it down where it's x squared equals k, but you can actually generalize this to where it's any algebraic expression. Okay, so that's what we're going to have here. We want to isolate the thing that's squared, which is the quantity x plus 5. So for number 4 here, we have 3 times the quantity x plus 5 squared equals 36. So we'll divide by 3. So we have x plus 5 quantity squared is equal to 12. And then what we can do is we can apply the square root principle to this part, right? So rather than having x squared, we have an algebraic expression squared. But when we apply the square root principle here, we're just going to end up with x plus 5 is plus or minus the square root of 12. Does that make sense? So we have x plus 5 is plus or minus the square root of 12. Again, that's by the square root principle. And then we just subtract 5 from both sides. So that leaves us with x is equal to negative 5 plus or minus the square root of 12. And I think we can just type that in as is, and that will give us the answer. I wonder if this is slash PM. No. No. There's like, if you hover over these, normally it'll tell you like the command. Yeah, so it's not plus. I don't know if you can read this, but it actually says slash plus minus. So if you get in the habit of doing these so often where you don't want to use the mouse and click them, there's actually a keyboard command that will do any of the things that you want to actually click. Because these are all typeset using LaTeX. Okay, so it didn't accept what we had there. Did I make a mistake? 36 over 3 is still 12, yeah? Maybe it just doesn't like it. Let's see if we use commas if it works. Negative 5 minus square root 12. Only other thing I could think of is maybe it wants it in simple radical form, because square root of 12 can also be written as 2 square root 3. So we'll see. The syntax on here is not always perfectly consistent. Not in the correct form. Okay, does it say simple radical form? It says the answer is correct. Oh, it says simplify, so they probably want 2 square root 3. So that's it. So let's go ahead and note that over here. And the reason is square root of 12 is the same as the square root of 4 times 3, which is the square root of 4 times the square root of 3, which is 2 radical 3. I believe that's from Module 2. Simple radical form. Any questions on that? Is that clear? Okay. Number 5 gets into some complex numbers. We won't do too much with complex numbers in this course, but it does come up on a couple of questions. How many people in here have seen imaginary numbers before? Oh, almost everyone. So that's good. Okay, well then it shouldn't be too much trouble. Essentially, there's a bigger field than the real number field, and that's the complex number field. So, what's the best way to say this? So, let's say the number I is the positive solution to x squared equals -1. So that is, we could think of I as equal to the square root of -1. So, for example, the equation x squared equals -25 has solutions. X is equal to plus or minus the square root of -25. And we could think of this as plus or minus the square root of 25 times the square root of -1. And that square root of -1 you can replace with that imaginary constant I. So this would be plus or minus 5I. So those would be the solutions. We're not going to go into more depth than that, so you can, for all purposes in this class, just think of I as the square root of -1. So it exists and it manifests itself in a lot of phenomena, specifically in electrical engineering and lots of other branches of math and science. The word imaginary is just terminology, so you don't want to think about it as something that's like ethereal or not existing. A lot of times you'll hear high school teachers explain it that way, which is not scientifically really accurate. Anyway, so let's go ahead and solve this actual equation. But yeah, we're not going to try and think of it too much more than in terms of solving a few simple quadratic equations. So for this one, we have x plus 2 quantity squared equals -64. So we start off kind of similar to the example I just showed. We use the square root principle, so we get x plus 2 is plus or minus the square root of -64. And then that's going to break down into x plus 2 as plus or minus the square root of 64 times the square root of -1. So we're going to get plus or minus 8i on the right-hand side. So we get x plus 2 is plus or minus 8i. And then we're going to subtract 2. And I kind of is the same thing as like if you're trying to add like 2 with x or something like that. You can't put them together, right? They're not like terms. So you can only add numbers that have i's if they both have an I next to them. So the same rule for adding coefficients of like terms applies. So we subtract 2, and we get x is -2 plus or minus 8i. And this should be our two solutions. Okay, did I botch something up? Yeah. Use a comma to separate. Maybe it doesn't like the plus or minus. Oh. Thank you. That's quite silly. Where did I get the 2 from? I just hallucinated it. That's a weird mistake to make, huh? Thank you. All right, there you go. I got a little, is there a word for like dyslexia with numbers? Maybe. Maybe that's just a branch of dyslexia, I don't know. Okay, so now we're going to talk about the perfect square, completing the square. So if you combine the strategy of the square root principle with this notion of completing the square and you put them together, you get a formula for solving every single quadratic equation known as the quadratic formula. So we're going to do a few completing the square examples. In general, once we learn the quadratic formula, you can always use the quadratic formula for solving examples with only numbers. But it's good to kind of see this method. Okay, so number 6 here. So the idea, so completing the square, let's talk about the idea. So the idea comes from this. If you have something that looks like x squared plus bx, you can add something to it that will make it factor into a perfect squared expression so that we can use the binomial square. So if we add, and if you had an equation, you'd have to add it to both sides, but we're just going to see how it works with this expression. So it's kind of like a magic number, b over 2 quantity squared. Then what happens is this x squared plus bx plus b over 2 quantity squared, this will factor into exactly x plus b over 2 quantity squared like that. And then you can apply the square root principle. You can check that by multiplying out, foiling out this right-hand side because it's a binomial times a binomial. You get x squared from the first term, b over 2x plus b over 2x, and b over 2 plus b over 2 adds up to b. So that's how you get the middle term. Then the last term is just itself squared. So that's the whole idea. It's a little abstract with the letters. Let's make it concrete with these numbers here. So if we have this x squared plus 12x, b is like the number 12 here. So if we just follow exactly what we did with the letters, 12 over 2 squared, which is 6 squared, that's 36, then this should factor x squared plus 12x plus 36. It should factor into what? X plus 6 times x plus 6, which is x plus 6 quantity squared. So the constant we're adding is that number 36. That's what they're asking for here. The trinomial is the, not factored, is the x squared plus 12x plus 36. And then we have the factored result. And in a moment, we'll see how we can use this to solve some equations that do not factor and don't immediately. Yeah. So this is going to be a similar type question. It's just going to involve some fractions, right? So let's go ahead and go through it. So here we have x squared minus 15x. So the thing that's acting as b, the letter b in this problem, is negative 15. So if we add negative 15 over 2 quantity squared, which is 225 over 4, then what happens? X squared minus 15x plus 225 over 4. How will it factor? Well, this thing that you're squaring is always the number that goes in the factorization. Does that make sense? So we're squaring negative 15 over 2, so that means the thing that it factors into is going to be x minus 15 over 2. So you don't have to refactor it in your head and use all that brain power. You can just say, okay, I'm immediately given the numbers that work with this completing the square process. All right. And the reason it works is because it works with those letters when you do the algebra up above. So once you understand the algebraic backing, then you don't have to keep doing all this arithmetic. So we're adding 225 over 4. And our trinomial is this x squared minus 15x plus 225 over 4. And then we have the binomial square, x minus 15 over 2, quantity squared. Does that make sense to everyone? So no real solving there. It's just trying to get you in the mode of figuring out what number you add, how it factors. That's the idea. Now, hopefully we'll see in the next question how it applies to some equations. Okay, so now we have a setting where we can apply this idea to an equation to actually solve a concrete problem. So x squared minus 6x, so this is just a solve. So how can we do it with an equation? Well, the first step is to keep all the x's on one side of the equation, and then go ahead and move the numbers to the other side. So that would just amount to adding 4. So we have x squared minus 6x equals 4. So now the left-hand side is kind of just like what we were doing, right? We were finding that special number and adding it to both sides. So that's what we're going to do now. Add negative 6 over 2 squared, which is what? Negative 3 squared, which is 9, to both sides. Okay, so we do that. X squared minus 6x plus 9 is equal to 4 plus 9. So that's going to be 13. And then what will the left-hand side factor into? Well, it'll factor into x, and then this number here, the minus 6 over 2, which is minus 3, right? So it'll factor into the quantity x minus 3 squared. And now what is this? This is one of those square root principle problems, right? We can say, okay, x minus 3 really has to be plus or minus the square root of 13. So we're building on the square root, and that's exactly where the quadratic formula comes from. So you'll start to notice the more complicated these problems get, the more they look like that, those answers that are negative b plus or minus the square root of b squared minus 4ac all over 2a, right? So x minus 3 is equal to plus or minus the square root of 13. Add 3 to both sides. So we get x is 3 plus or minus the square root of 13. So for simple problems, a lot of times this even works faster than plugging everything into the quadratic formula. Makes sense? How many people have seen completing the square before? I still teach a lot, not so many. So, it's like half and half. I think a lot of people that come from high school math, they're just like given the quadratic formula and they say, okay, it works, go ahead and use it. But I do think this is pretty interesting. It's not so formal of proof, but really the proof works exactly the same way if you apply it to solving ax squared plus bx plus c equals 0. Okay, I don't know if this one contains radicals, or I, but some of these potentially will contain I, and that happens when, right, you end up with the square root of anything negative. So here we have x squared minus 10x plus 29 equals 0. So we subtract 29 from both sides. So x squared minus 10x equals minus 29. Once the x's are on one side, everything else is on the other. This is where we figure out the special number to add. So add negative 10 divided by 2 squared, which is negative 5 squared, 25, to both sides. So we get x squared minus 10x plus 25 is negative 29 plus 25. So the left-hand side will factor into x minus 5 quantity squared. And the right-hand side, we end up with negative 29 plus 25, which is negative 4. So at this point, we can tell that we're going to have imaginary numbers in our solution, right? Because this is the part where we're going to have to take the square root, and on the right-hand side, we're going to end up with the square root of negative 4. And anytime you're taking the square root of a negative, you're going to end up with an I in your answer. Does that make sense? So by the square root principle, x minus 5 is plus or minus the square root of negative 4. So the square root of the negative is what gives you the I, and then the square root of 4 gives you 2. So the right-hand side is just plus or minus 2i. And then to get our answer, that's all we have to do is add 5. X is 5 plus or minus 2i. Yes. So we always take the middle number, the number in front of the x, the negative 10. We divide it by 2. So the negative 10x here, we look at the negative 10. You divide it by 2 and then you square it. So negative 10 over 2 is negative 5. Negative 5 squared is 25. That's like the magic number we add. So it's always a two-step process. Look at the number in front of x, divide it by 2, and then square it. And then that's what you add to both sides. So you can think of this completing the square process as put all the x's on one side, add that magic number to both sides, and then you should get it to factor like this. Okay, so now we're going to jump into things where we talk about the quadratic formula. So I'll write down the quadratic formula for you. So again, if you're uncomfortable with completing the square, you'll be able to go ahead and use the quadratic formula for the most part, unless the question is framed like it was before. Like, what number do you have to add? How does it factor? And then so on. So some of them are written specifically for completing the square, but when it comes to solving equations, you can kind of always use the quadratic formula. So for number 10 here, let's write down the quadratic formula. So quadratic formula. So basically it says the solutions to. So when you have the equation, you want everything on one side and 0 on the other. You have to set it up that way before you can start doing the quadratic formula. So you have to write it as ax squared plus bx plus c equals 0. And then r, and then we get x is negative b plus or minus the square root of b squared minus 4ac over 2a, right? So like if you're looking for a last minute Halloween costume, you should just buy a t-shirt with this on it. Probably scares more people than most Halloween costumes that people dress up as. Okay, so two things when you apply this that usually trip people up. If b happens to be a negative number, negative b would be a positive number. And then when you're squaring something, you need to put it in parentheses. Okay, so if you have a negative value, that b squared needs to be in parentheses. A lot of people will mess that up. So they're talking about the discriminant here. The number that's underneath the radical, that is known as the discriminant, and it will tell you what types of solutions you have. So b squared minus 4ac is called the discriminant. I don't know why they came up with that term, but I'm guessing just because it discriminates what type of solutions you have. there's three possibilities for solutions to a quadratic equation. Either two real solutions, one real solution, or two complex solutions. So if b squared minus 4ac is a positive number, there are two real solutions. If b squared minus 4ac equals 0, there is one real solution. And if b squared minus 4ac is negative, there are two imaginary solutions. Okay. So in this example, we have x squared minus 6x minus 6 equals 0. So to figure out the discriminant, you need to identify a, b, and c. So a is the number that's in front of the x squared, which is 1. B is the number with x, which is negative 6. And c is the constant term, which is also negative 6. So b squared minus 4ac here. And again, this is what I'm talking about. When you have negative 6 and you're squaring it, you need to put parentheses around it. Otherwise, you'll get the wrong answer. So you have negative 6 squared minus 4 times 1 times negative 6. So this comes out to 36 plus 24, which is 60. So from what we wrote down, this will have two distinct real solutions. So our discriminant here is 60. And so there are two unequal real solutions. So that's the discriminant. Okay, so use factoring to solve the polynomial equation. So this will mix in some of the factoring that we know, possibly with some other methods. Six x to the fourth minus 54x squared equals 0. So we want to look for the GCF here, which is going to be 6x squared, right? Both 6 and 54 are divisible by 6, and they both have at least an x squared in common. So we have 6x squared, and we'll be left with x squared minus 9 equals 0. And then, does anyone remember how x squared minus 9 should factor? That is difference of squares. Remember, if you have a squared minus b squared, that factors into a plus b times a minus b. So x squared minus 9 should factor into x plus 3 times x minus 3, because 3 squared is 9. And then you can use the zero product principle on each part. Three things multiplied together that are 0, one of the three factors must be 0. So 6x squared equals 0, or x plus 3 equals 0, or x minus 3 equals 0. So the only way 6x squared is 0 is if x is 0. The middle part you would subtract 3, so x has to be minus 3. The last part you have to add 3, so x would be 3. So we have 0 or plus or minus 3 as our three answers here. Does that make sense? So I'll set there. Okay, so again, another factoring one. We're going to put everything on one side. This one has 4 terms, and we haven't learned any real 4-term things you can't always factor. But when we factored quadratics, we did decompose them into a four-term thing. And what we did after that was we factored by grouping. So kind of when we have something with four terms, the thing we would look to do is factor by grouping. And if that doesn't work, we might not be able to do it by hand. We might have to appeal to like graphing or something like that. But usually on these, we'll be able to factor by grouping. I'm just trying to say it doesn't necessarily always work for every problem. But so we have x cubed plus x squared equals 16x plus 16. So I want to get everybody on one side. So I'll subtract 16x minus 16 on both sides. So I end up with x cubed plus x squared minus 16x minus 16 equals 0. And now I can group, right? So I'm just going to look at these guys as one group and these guys as one group. And I'm going to say, do you have anybody in common that I can take a GCF out of? So x cubed and x squared, you can take an x squared out of both of those. So if I take out x squared, I'm just left with x plus 1. X times x squared gives me the x cubed. And x squared times 1 is the x squared. And then the second group, I can take out a minus 16. And minus 16 times x is minus 16x. And minus 16 times positive 1 is minus 16. So now what's happened is I've got that x plus 1 with both terms, so then I can factor. So I'll have my x squared minus 16, the numbers in front, and I'll also have the x plus 1. And one more step to finish this one. The x squared minus 16 is a difference of squares, so that can be factored into x plus 4 times x minus 4. So x plus 4 equals 0, or x minus 4 equals 0, or x plus 1 equals 0. So I get x equals negative 4, or x equals positive 4, or x equals minus 1. So those are the three answers there. Any questions here? Okay, so now we jump into some radical equations. So for radical equations, the strategy is simple. Just isolate the radical. And I'm going to say square both sides, but for instance, if it was a cube root, you would raise both sides to the third power. So depending upon the radical, you're going to raise both sides to a power. But most of the time it's going to be a square root, so you just square both sides. Now the thing about radical equations that doesn't happen with the ones we were just looking at, the polynomial equations, is we always have to check our answers for these ones. So I'm also going to say check answer or answers in the original equation. So why do we have to do that? Well, the answer here is squaring equations may introduce extraneous solutions. So extraneous solutions are, when you square something, you make it more complicated, right? So you might be adding solutions to a new, more complicated equation that wasn't really a solution of the simpler thing that you started with. For instance, let's think about a very easy equation. Let's think about x equals 3. Well, that's already solved, right? X equals 3 only has one solution. 3. It's solved. Done. What if we were to square this equation? What would we get? X squared equals 9. Now, while that's still true, how many solutions does that equation have? It has 2, doesn't it? From the square root principle. Positive 3 or negative 3. So in this case, this has solutions x equals plus or minus 3, but negative 3 would not satisfy the original equation. Negative 3 is not the same thing as 3. So we would say negative 3 is extraneous. So that doesn't work in the original equation. So squaring equations makes more complicated things in some sense, so you have to check. But for practical purposes, it's kind of the only way to get rid of the square root. So you kind of have to complicate the equation to solve it. Okay, so we have square root of 2x plus 13 equals x plus 5. So we square both sides, right? So square both sides. Radical's already isolated. So squaring on the left cancels with the square root. So we just get 2x plus 13. And on the right-hand side, you want to FOIL it out. So that is x squared. Outside is 5x, inside is 5x, so that adds up to 10x. And then 5 times 5 is going to be your 25, right? Recall x plus 5 squared is really x plus 5 times x plus 5, which is x squared plus 5x plus 5x plus 25, which is where we're getting our x squared plus 10x plus 25. To expand a squaring up binomial, you always have to FOIL out like that. So that's where we got the x squared plus 10x plus 25. Now we're going to have a quadratic equation. Get all the terms on one side. Try and factor it. If it doesn't factor, then we use the quadratic formula. That's what we've learned today. So I'm going to subtract the 2x and also the 13. So it's 0 equals x squared plus 8x plus 12. And luckily this one factors, right? 2 times 6 is 12, and 2 plus 6 is 8. So this will factor into x plus 6 times x plus 2. And we get two answers there, right? X equals negative 6, or x equals negative 2. All right, so we've now gone through all the steps and solved this radical equation. Last thing we have to do is check our answers up here in the very first line. Square root of 2x plus 13 equals x plus 5. So we have to check both answers and see if they work. So let's check negative 6. The square root of 2 times negative 6 plus 13. Does that equal negative 6 plus 5? Well, you would have the square root of 1. Does that equal negative 1? It does not. So negative 6 is extraneous. And then we also want to check the negative 2. So we'd have the square root of 2 times negative 2 plus 13. And we're asking, does that equal negative 2 plus 5? Well, we're getting the square root of 9. Does that equal 3? Yes, it does. So negative 2 is our only solution here. The negative 6 turns out to be extraneous. Okay? Ah, this one's complicated. The reason it's complicated is because we have two radicals. So when you have two radicals, sometimes you have to square the equation twice. How do you know which radical to isolate if you're going to have to square the equation twice? Usually you want to isolate the more complicated of the two. Does that make sense? So which is more complicated, the square root of x or the square root of x minus 9? The square root of x minus 9. So this is one of the harder problems on the homework. So if you're a little bit lost on this problem, that's okay. I would try and go through all the other ones first and then maybe come back to this problem if it's confusing. If it's confusing, that's okay. So usually on the homework there's a problem or two that are a little more complicated than the things you see on the test, which is fine. Okay, so let's start by subtracting that square root of x. So the square root of x minus 9 is equal to 1 minus the square root of x. So now we've isolated the more complex radical, so this is where we're going to square both sides. So we square the square root of x minus 9. That will equal 1 minus the square root of x quantity squared. So on the left we have x minus 9. Now on the right we're going to have to FOIL this the same way as before. So you have 1 minus 2 square root of x, and then you're going to have minus square root of x times minus square root of x for your last term, which is just a plus x. So you might think maybe we didn't make any progress, there's still a square root, but at least now there's only one square root left in the problem. So now we can isolate that square root and then square everything. So how do we do that? Well, let's add the 2 square root x to both sides. So 2 square root x plus x minus 9 equals 1 plus x, and then we'll subtract x and add 9. So the left now is just 2 square root x, and on the right hand side we only have 10. The positive x and negative x cancel, and then we just have the two numbers. So it's actually simplifying quite nicely. So divide by 2, we get the square root of x equals 5. Square both sides, you get x equals 25. So then we just need to do the check. So we're checking in this equation over here, square root of x plus square root of x minus 9 equals 1. So you have square root of 5 plus the square root of 5 minus 9 equals 1. This would be the square root of 5 plus the square root of minus 4. Does that equal 1? I don't think so, because this is the square root of 5 plus 2i. That's not equal to 1. So that solution doesn't work. Well, that was our only candidate solution. If it didn't work, that means this equation actually has no solutions. So that's probably why no one complains about this problem, right? They just, since you have unlimited attempts before the deadline, you just check to see if it's the empty set. And then if it is, you don't ever have to do the problem. Oh, I meant to do next. That's some more. Wait, I think I clicked the wrong thing. Save this attempt. I clicked save this attempt, not save best score. I mean, not that it matters, I'm not. Okay. Rational exponents is going to be similar because you can think of every radical as a rational exponent. What you have to do is you just have to raise both sides to the reciprocal power. So same sort of thing here. You want to isolate the x and then raise it to the appropriate power to isolate x. So let's see how that goes here. So we have 7x to the 5 over 4 minus 77 equals 0. So let's add 77. So x to the 5 over 7x to the 5 over 4 is 77. So divide by 7 to get x by itself. So we have x to the 5 over 4 equals 11. And now I claim if you raise both sides to the power of 4 over 5, that will give you the answer, right? Why is that? Well, the reason is when you raise an exponent to an exponent, what do you do with the exponents? You multiply them, right? And the multiplicative reciprocal of 5 over 4 is 4 over 5. So if you multiply the 5 over 4 with the 4 over 5, you just get the first power. So the left-hand side just becomes x. And then this is 11 to the 4 over 5. And I think that's all they want. You could write that in radical notation if you want, but remember, if you have a fraction as an exponent, the bottom number is what kind of root it is, and the top number is what the power would be. So this would be the 5th root of 11 to the 4th power. Okay, so this one's similar. We'll probably stop here for this week and then finish the last 15 next Wednesday. But let's go ahead and do this one. It's going to be very similar. Finish just over half. We'll also take a look at the algebra activity after this. So for number 16, we have quantity x minus 5 to the 2/3 equals 100. So we want to raise both sides to the 3 over 2 power. So then when you multiply those exponents on the left-hand side, they go away. You just get 1. So we have x minus 5. On the right-hand side, this is the same thing as taking the square root of 100 and then raising it to the 3rd, right? Because the bottom number is the root, and the second root is the same as the square root. So this is the same as 10 to the 3rd power. And 10 to the 3rd power is just 1,000. So when you add 5, you get x equals 1,005. That would be your answer. Yep. We forgot to check our answer, but does that the 3rd root is... I'm just looking at checking the answer. If you had 1,005 minus 5, that's 1,000. The 3rd root of 1,000 should be 10, and 10 squared should be 100, so it looks like it works. That's strange. Am I missing a second solution somehow? How could that be? We're not taking a square, we're taking... Square root of 100 is 10. 2 to the third power, just 3 zeros. 1,000. That's 5. Anybody see anything here? There should be 2? Okay, so let's think about that. There should be a negative? Where did I take a square? So technically, I'm taking a square root here. So let's do it in 2 steps. Let's go ahead and do 2 steps instead of doing it in 1. Since we are technically squaring it if we're... Well, let's just see. Right, I'm not applying the square root principle. This is what's happening. So if let's cube it first. Let's do this in 2 steps. So let's do the x minus 5 to the 2/3. Let's just cube both sides to start. So I would end up with x minus 5 squared. And then this number would be 6 zeros, right? So I have x minus 5 quantity squared is 1,000,000. Okay? So this one you have to do in 2 steps because here I now have something squared, right? And when you have something squared, you have to apply the square root principle, which should have a plus or minus as the solution. So that was the implicit mistake I made there. I did everything in 1 step and forgot that the square root principle was in play. If it were reversed, maybe I could get away with it. So now I should get x minus 5 is plus or minus the square root of 1,000,000. So 1,000,000. So x minus 5 is plus or minus 1,000. So this is 2 equations. X minus 5 equals negative 1,000. Or x minus 5 is positive 1,000. So when you add 5 to negative 1,000, you get negative 995. When you add 5 to positive 1,000, you get the 1,005 that we got. So we missed the solution, negative 995, by trying to do the reciprocal exponent in 1 step rather than in 2. So the original way we did it, we made an error. Easy to do. Easy to do. That makes sense? Okay, why don't we have a look at the algebra activity, and then after that we'll stop for this week, and if you have any questions I can come by and try and answer those. So the algebra activity is also on my Math Lab 1 this week. So it's just under the homework. Okay, so this one you're just watching videos and then answering some questions. So nothing too hard there. You just open and then watch the video talking about linear versus nonlinear relationships. Okay, same thing. You're just identifying linear, quadratic, and quartic. We probably could have done that in one of the early modules. Remember, the degree of a polynomial, which is something we talked about, corresponds to those different things, right? Probably you can guess this first one's linear. We're solving quadratics today, which means the degree 3 has to be the cubic. Okay, yeah. Okay, so I won't say too much about this because in all of them you should just be able to answer from the video. So if you get stuck, just let me know next week. But watch the video and you should be able to answer all the questions. Just 5 questions. Nothing too difficult there. All right, does that sound good? So we'll stop here and we'll go over the second half of the homework next Wednesday. Finish. Oh yeah, let me do it.